Welcome to the series of 3 podcasts, Reaction Prediction 1, Reaction Prediction 2, and Reaction Prediction 3. The learning objective for these 3 podcasts is you should gain a good understanding of how to write balanced net ionic chemical equations at AP chemistry level. In the first podcast, I'm going to go over a quick review of naming inorganic compounds and what are net ionic equations and how to write them. In the second podcast, I'm going to go over types of reaction, and in the third podcast, I'm actually going to be doing practice problems with you on writing reactions. The resources that you need for these three podcasts are 2 worksheets. The first worksheet is what is projected on the screen here. It's called Reaction Prediction 2012, and the second worksheet that you need is called Naming Inorganic Compounds. Both these worksheets are uploaded with the podcast for your reference. So before you can do successful reaction prediction, you must know your solubility rules. This hopefully you covered in first year of chemistry, and they're also given here. And these have been very simplified. There are many more solubility rules, but I have only listed here the ones that you commonly use. The second thing is you need to know how to name compounds. And then you need types of reaction, which I'm explaining later in second podcast, and how to write net ionic equations and what they are, which is covered at the end of this podcast. So let's start this podcast with a quick review of naming inorganic compounds. Oftentimes, students find reaction prediction very hard because they have forgotten how to name a compound, or if ferrous sulfate is written, they don't know how to write it in chemical formula. Before you can do reaction prediction, you must review your naming. Naming is like knowing your words before you can write sentences or go on to write an essay. For naming purposes, to simplify naming rather, I have classified compounds in 3 big categories: ionic compounds, molecular compounds, and acids. Ionic compounds are compounds that have a metal in it, a metal cation. Molecular compounds lack a metal cation, are made up of all nonmetals. And acids generally are compounds that begin with H. Now let's look at each of these and how to name them in detail. Another thing I want to bring up here before I go into naming is ionic compounds are present generally as solids in natural state. Molecular compounds are generally present as liquids and gases, even though they can be present as solids as well. And acids are generally present as solutions or gases. That was just so that you remember these. Now going over ionic compounds. To name an ionic compound, you name the metal cation first. The positive or the cation is always written first in an ionic compound, followed by an anion, which is negative. Generally, in an ionic compound, it may look like this: NaCl, K2SO4. But sometimes ionic compounds may also look like KHPO4. K2HPO4. Now these are all binary compounds. What does it mean? It means it has 2 parts. Now 2 parts are easier to see in first 2 examples: NaCl plus and minus. K2SO4, K is the cation, SO4 is minus. But some kids get confused and think in K2HPO4 you have 3 uppercase letters, right? So some kids think, oh, there are 3 things present. Incorrect. There are still only a cation and an anion present in K2HPO4. All compounds, all ionic compounds that you'll come across are binary, and the rule for naming them is the same. You name the cation first, followed by anion. If your cation shows variable valency, meaning your cation is one of the transition metal cations, then you need to specify the charge on the cation. There are 2 ways of specifying this charge. Either you can use parentheses with Roman numeral inside, Or you can use the old way of nomenclature, which is us-ic-way. Let me go over each of these quickly with you. Let's say you're given an example of FeSO4. Now you know, once you've memorized, you will know that iron sulfate's charge is 2-, so iron should be 2+. And you would know, because you've memorized, that iron shows two oxidation states, 2+ and 3+, and lower of the two oxidation states is called us. So iron's old way of naming is ferrous, so we'll name it ferrous sulfate. Or the stock way of naming this will be iron, and within parentheses 2, specifying the charge on iron, sulfate. Well, if you had Na2SO4, you'll just name it sodium sulfate. The list of common cations with variable valency are given here. There are many transition metal cations that show variable valency, but to memorize them is an overkill and you won't be able to do it. So these are the common ones that are used at your level. Now, talking about ionic compounds again, how do you name an ionic compound? How do you write the formula if the name is given to you? If something said sodium sulfide, what you have to do is use crisscross method, sulfide, and in crisscross method what happens is you write the name of each of the ions. Like sodium is Na, and you know it tends to form +1 cation. Sulfide, sulfur being from group 16, tends to form 2-, and you crisscross the charges, becomes Na2S1. We don't write ones in chem, so its formula is Na2S. So to write formula from the name, you use crisscross method, where you bring the charge of one ion next to the charge, as a subscript next to the other ion. Similarly, ammonium chloride, you would have memorized that ammonium is NH4 with a +1 charge, chloride is Cl with a -1 charge. You crisscross them and it is ammonium chloride. What if it was ammonium sulfate? You know, ammonium forms +1 and sulfate is SO4 2-. When there is a polyatomic ion, you generally put a parenthesis before putting the charge, showing that this whole formula is repeated twice. So it's NH4 twice, SO4. Now, how to name a molecular compound? To name a molecular compound, the first element is followed by its oxidation state in parentheses, or you can use older way of naming compounds. So if you have CO2, which is carbon dioxide, you have two ways of naming it. In the old way or prefix way, you name your first element, which is carbon, and then you write di to show that there are two oxygens, and then you say oxide. One note here, you don't write mono before the first element, but you do write mono in between. So if it was CO, you'll name it as carbon monoxide. So mono can come in between but not before. Now, how to name it the stock way? In the stock way, you take the oxidation state of the first element, and please review your oxidation states. Carbon's oxidation state in this case is 4, so you name it as carbon 4 oxide. So this is how you name molecular compounds. So there are two ways of naming ionic compounds: old way, us-ic way, or just using charge within parentheses. Similarly, there are two ways of naming molecular compounds: prefix way, which is using mono-di-tri, or using stock system. Now, how to name an acid? There are two types of acids. Acids that are oxyacids have oxygen in them, like HClO4, HClO3. These all have oxygen in them, so they're oxyacids. Or HCl, HF, that don't have oxygen in them. How do you name these acids? Naming of acids that don't have oxygen in them, like HCl, HF, is rather easy. you name them starting with hydro and end them, and then name the anion, which is fluoride, but instead of fluoride you add ic acid, so its name becomes hydrofluoric acid. Similarly, HCl is hydrochloric acid, and so on. If oxygen is present in an acid, then the naming of acid depends upon the cation that forms this acid. For example, in HClO4, it is again a binary compound formed from H plus ion and ClO4 minus cation. So ClO4 minus cation, what is the cation's name? It's perchlorate. If the anion ends in ate, then the acid's name is ic acid. So if the anion is perchlorate, the acid's name is perchloric acid. Please note that we don't use hydro with oxy acids. Now, naming complexes. The way to name complexes is you name the cation first, followed by anion, and within a complex you name the transition metal and you specify its charge within parentheses. And then you name the ligand ending in "ide" or whatever. If it is a polyatomic ion, then whatever its ending is. One thing, before naming the transition metal within the complex, you name the ligands first, and these ligands are named in alphabetical order. If you have more than one ligand of the same kind, you can use a prefix, di, tri, and so on, but prefixes don't count toward alphabetizing the ligands. And there is a whole another lecture on naming ligands, so I'm not going to go over in detail here. You can refer to my website later on for that. This is a handy dandy list of common cations that with variable valency that you'll need to memorize, and this is a pretty comprehensive and shortened actually list of polyatomic ions that are must memorize at AP chemistry level. And here are some practice problems where I've given you some names and some formulas. See if you can write the names. Without naming, you will not be successful at writing reaction prediction. Please remember, naming is like being able to write words. You must know how to write words before you can write your sentences. So hopefully this was a quick review and you got a quick refresher on how to name compounds. Now let's go back to the other document, which is RP 2012, Reaction Prediction 2012, and look over what is a net ionic equation, because at AP chemistry level you're required to write a balanced net ionic equation. Balancing you all understand, but what is net ionic equation? A net ionic equation is the one that does not have spectator ions in it. Spectator ions are ions that are present both in reactants and products and remain unchanged during a reaction. So you cross it out. The key to writing net ionic equations is to be able to differentiate what dissociates or breaks when writing an equation and what doesn't. And there are some guidelines here that I would like to go over before I start writing net ionic equations with you. These are some of the things that I have observed over my years of teaching of commonly made mistakes. So I have put them as bullet points here. First thing, you always need to write balanced net ionic equations for AP chemistry exam, meaning dissociate everything that is dissociable based upon solubility rules or based upon whether it's a strong acid or a weak acid, and do not dissociate what cannot be broken, like precipitates cannot be dissociated. Next thing, pure metals, Ag, Cu, any of those that you see as alkali metals, alkaline earth, or transition metals, they are insoluble and are atomic. And you write it with a parentheses S for solid, meaning it does not dissolve. Like if a reaction says magnesium reacts with hydrogen, you'll write magnesium as Mg with a solid sign. At this, I would like to jump over to this point number 9. Mg is not the same thing as Mg2 plus. Remember, Mg is an atom. Mg2 plus is an ion. When the atom loses electron, it forms the cation. So you cannot cross out Mg2 plus with Mg because they are not the same species. Similarly, zinc and zinc 2 plus ions are not the same species. Do you think you get it? That's my joke for you. The next one, molecular compounds. And remember, how do you identify molecular compounds? By the absence of a metal in it. So any compound that has all non-metals, CO2, H2S, N2O5, SO3, all of these are molecular compounds. They are gases, they are written with G, and they do not dissociate. Pure water is written with liquid sign, and it does not dissociate. One comment here, you do not need to write states of substances on the AP exam and in most AP Chem courses, though it may vary from teacher to teacher, but I encourage my students to write the states because it helps clarify what they are breaking and what they are not breaking based upon this. Now, ionic compounds, so you know molecular compounds never break, you know metals never break. What about ionic compounds? Ionic compounds may or may not break, and that is guided by what's called solubility rules. So solubility rules are for ionic compounds. Solubility rules dictate that these things are always soluble, meaning any ionic compound that has an alkali cation, like first group cation, K2SO4, NaCl. Irrespective of what N ion this K and Na are bound to, they'll always be soluble. So the moment you see K plus or Na plus in a compound, you know it's soluble. Similarly, if you see ammonium or nitrate or chlorate or perchlorate or acetate, you know these are always soluble. Doesn't matter what their other half is. As long as they have these ions, the compound becomes soluble. Generally solubles are chloride, bromides, and iodide, but there are exceptions to them. Any compounds that contain silver ion as the cation with chloride, bromide, iodide is not soluble because it's an exception to solubility. Any ionic compounds that contains Pb2 plus with Cl minus, Br minus, or I minus is insoluble. Any compound that contains mercurous, Ag2 2 plus with Cl minus, Br minus, I minus becomes insoluble, and so on. So let's take some examples here. I'm sure you can read through the rules and make sense of it once you see the pattern. So do you think PbSO4 is soluble? Now, what would you do? You'll go to SO4 and sulfates, says generally soluble, but exceptions are calcium, strontium, barium, and lead. So if lead is an exception to sulfates, is it soluble or not? No, it's not soluble. Another little mnemonic thing I want to tell you, how to remember exceptions here. APH, I call them as APH. You take AP classes and honors classes, so think of this as APH, and they are all in their lower oxidation states as Pb2 plus and Ag2 2 plus. It is mercurous, not mercuric. Similarly, the exceptions to sulfate, think of Cb as the new station and Pb as the new station. Bs is all Bs, so we just consider it once, but C for calcium, P for Pb, B for barium, S for strontium. And similarly, CBS here is the exception. So these will help you memorize your solubility rules. I'm going to do a couple quick practice problems on solubility rules before I move on. Is calcium nitrate soluble? Yes. Why? Because the moment you have nitrate in a compound, it makes it soluble. Is calcium chloride soluble? Yes, because all chlorides are soluble except for these, and calcium is not one of those. Is strontium hydroxide soluble? No, because hydroxide, I'm wrong. This is soluble because hydroxides are generally insoluble, but if it is strontium, calcium, or barium's hydroxide, that makes it soluble. So strontium hydroxide is soluble. And you'll learn later that it's a partly soluble compound. Now, what if you had sodium hydroxide? Will it be soluble or not? It will be soluble. Why? Because even though hydroxides are insoluble, there is sodium in it to make it soluble. So that was solubility rules. So you know what to do with molecular compounds. They don't dissociate. Ionic compounds may dissociate depending on solubility rules. What about acids and bases? Strong acids, and you must memorize this list. These acids always dissociate. And strong bases, group 1 and 2 hydroxides except for beryllium and magnesium are all strong bases. They dissociate. Weak acids and base, we don't dissociate in net ionic equation. There's an equilibrium which will be covered in weak acid base situation. Now going to this point, remember P.S. Hofbrinkel. These are the elements that don't exist as monoatomic. Phosphorus, P, exists as P4. Sulfur exists as S8. And hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and fluorine, each of these by themselves exist as diatomic gases. Now, commonly in practice, phosphorus is just written as P, not P4. So you'll see some resources, phosphorus being written as P. In some resources, it's written as P4. Sulfur as S or S8. My preferred mode is P4 versus P, or S8 versus S. And with that, I think you have enough background to practice writing some net ionic equations. So let's practice some net ionic equations here. Let me create some room here. Barium chloride, and if you know your naming, you know barium is Ba, chlorine is Cl, but chloride is Cl minus. Barium tends to form 2 plus, Cl minus, crisscross it, it's BaCl2. And it is aqueous, plus potassium sulfate, K2SO4. It'll be aqueous again because the question generally would say a solution of barium chloride and a solution of barium sulfate is mixed. What if the question said solid barium chloride is used? Then you will not dissociate it even though barium chloride can dissociate. You will only dissociate barium chloride if water is present in the system. Now it forms, as the reaction says, barium sulfate, which is BaSO4 and potassium chloride, and to balance it you put a 2 in front of potassium and chloride. Now this is your complete balanced equation. To write complete ionic equation, now you start breaking up what breaks. Barium chloride, because it's soluble. How do you know that? Because solubility rules tell you that you break them up as barium ion and 2 chloride ion. You don't write it as Cl2. Then you break it into 2K plus and SO4 2 minus. Again, a commonly made mistake is kids break it up as K2 plus SO4 2 minus. That's wrong. K does not occur as 2. It's only Hofbrinkel, right, that occur as diatomic. Potassium occurs by itself and has a +1 charge. So you got to write +1, but since there were 2 of potassium, you put a 2 in front of it, not as a subscript. Now barium sulfate, your solubility rules tell you that barium sulfate is insoluble, it forms a precipitate, so you don't dissociate it. And potassium breaks and chloride breaks. Now look for spectator ions. What are common on both ends? It's chloride and potassium. So the net ionic balanced equation will be Ba2 plus SO4 2 minus gives you BaSO4. And writing states is not mandatory. So that's the first example of net ionic equation. Now let's take another example of net ionic equation. Zinc plus hydrochloric acid. So when a metal is written by itself, is present in atomic form, it's insoluble. Hydrochloric acid is HCl, and you will know how to make or predict products in the next podcast, but for now we'll just write it. Zinc chloride, ZnCl2 plus H2, and to balance we put a 2 here. You know ZnCl2 Let's go back to solubility rules here. Chlorides are generally soluble and Cl is not an exception. So ZnCl2 is soluble. Let's go back down and rewrite that. So Zn solid plus HCl aqueous solution gives you ZnCl2 aqueous. If it had precipitated, we'll write S, and hydrogen, it's a gas. Now to write complete molecular equation, let's start breaking up what breaks. So zinc just remains as such. HCl being a strong acid will break, and we forgot a 2 here to balance it. So it'll be 2H plus 2Cl minus. And these dissociated, and ZnCl2 will be broken up as well because it's soluble, and H2 will be written like this. Now let's cross out spectator ion. Cl minus is the only spectator ion. Another commonly made mistake, sometimes kids cross out 2H plus with H2. Remember, these are two different species. H2 is a molecule, 2H H plus is an ion. You can cancel them out. So what's the net ionic equation? Zn plus 2H plus gives you Zn2 plus H2. So ultimately there was electron transfer between zinc and hydrogen. Hydrogen gave its accepted electrons from zinc. Zinc turned into zinc cation, and hydrogen ions turned into hydrogen gas. So that's the net ionic equation here. The last example of net ionic equation is with silver nitrate, and let's do this one as well. AgNO3, and you know all nitrates are soluble, so it'll be soluble, plus H2S gas gives you silver sulfide Ag2S plus HNO3. Now let's balance it. If you put a 2 here and a 2 here, that balances the equation. Let's break what can be broken. All nitrates are soluble, so let's break silver ion and 2 nitrates. H2S being a molecular compound will not dissociate. Ag2S, our rules say that sulfides are generally insoluble, and HNO3 being a strong acid will dissociate. Now let's cross out the spectator ion, which is nitrate. So your net ionic is 2Ag plus H2S gives you Ag2S plus 2H plus. I hope you got a good understanding of what net ionic equations are, how to write them, and a quick review of nomenclature. Thank you for listening, and I will be going over types of reactions in the second podcast.